Hi, it's Mr. Mac, and we're going to look at the structure of the atom. Well, we can't actually look at the structure of the atom. We're going to look at really important experiments that show us the structure of the atom.
Welcome to Mr. Mac's Physics channel. He can explain things really well and is a lot of fun to watch.
So this is the module from the universe to the atom, and it's the second inquiry question to do with the structure of the atom. And here are the outcomes. And you can see down the side I've put numbers that refer to the 5 different experiments that we need to know very well. The inquiry question is, how is it known that atoms are made up of protons, neutrons, and electrons? We're learning to assess the model of the atom with properties of the electron and the nucleus. And we'll be able to describe and assess experiments that give evidence for the nuclear model of the atom. Well, what were the important experiments? The first was by Crookes and his experiments with cathode rays. Secondly, we'll look at Thomson and the charge to mass ratio experiment with electrons. Next, we'll look at Millikan and his oil drop experiment to measure the charge of an electron. And then Geiger and Marsden, they performed the gold foil experiment under the direction of Rutherford, who developed the orbital atomic model. And lastly, we'll look at Chadwick and an experiment that led to the discovery of the neutron. Firstly, Crookes' experiments with cathode rays. So what are cathode rays? There were streams of glowing something. They didn't quite know what they were. They were observed in vacuum tubes, tubes that are glass and were evacuated and equipped with at least 2 metal electrodes, a cathode and an anode. The cathode they knew could be connected to a negative and the anode to the positive, and high voltage applied. And there were different shapes and ways that Crookes tubes were used to deduce the nature of cathode rays. Some had a Maltese cross put inside. There was a Crookes tube with a phosphorus screen. There was even one with a paddle wheel. And Giesler had different tubes at different air pressures. But what are the inferences that we can form? Just have a look at the equipment on the right-hand side. And the apparatus is a cone-shaped glass tube about 24 centimeters long, 84 millimeters in diameter at the thicker end, 48 millimeters diameter at the thinner end, with 2 terminals built into it. Mounted inside this glass tube is a Maltese cross that's hinged. It can flip up or back down flat. And when it's connected to an induction coil that supplies 50,000 volts DC, as you can see in the photo, a shadow of the cross can be seen at one end. The inference is that cathode rays travel in straight lines to produce this shadow. Cathode rays are also invisible, and yet at the end it causes a glow called phosphorescence when they hit the glass. The inference is that cathode rays can excite atoms. Although cathode rays occur regardless of the material that's used for the actual cathode, the metal at the end, and the inference is that cathode rays are independent of the material used. Cathode rays can be deflected by a simple bar magnet, and when a bar magnet is placed near the cathode ray tube, the cathode rays are deflected, and you can work this out very simply using the right-hand rule. The inference is that cathode rays are moving charged particles. And cathode rays can be deflected by electric fields. When oppositely charged plates are placed on each side of the cathode ray tube, cathode rays are deflected in the opposite direction to the electric field. The inference is very clearly that cathode rays are negatively charged, since they are attracted or repelled by an electric field. And cathode rays cause that paddle wheel to roll in the same direction as the cathode rays. And the inference is that cathode rays carry and transfer momentum. The second one we'll look at is the charge to mass experiment by Thomson. The aim of this experiment was to measure the charge to mass ratio of cathode rays. So a beam of cathode rays was initially fired and accelerated through 2 anodes called collimators, and you can see that in the diagram or the photo that I have on the bottom right. The collimator was basically a hollow tube of metal that was connected to the anode. The position of the dot then was noted on the phosphorus screen, which is on the right-hand side. The strengths of the fields are then adjusted so the beam was undeflected. So you can see that the cathode rays from this particular photo would go from the left to the right. So from this side to this side. And in the middle there were some electric plates inside the tube and two electric coils producing a magnetic field. And so those both were equal, so both fields are at right angles to each other, so the force due to the electric field equals the force due to the magnetic field. Or simply, QE equals QVB. Dividing both sides by Q, we have E equals VB, and rearranging, we have V, the velocity of the cathode rays, as a ratio of the electric field to the magnetic field. Well, then the electric field was turned off, and now the deflection of the beam was due only to the magnetic field. Thomson then measured the radius of this deflection, and the magnetic field caused the beam to curve in a path of a circular arc. Thus, the force due to the magnetic field equals the centripetal force, or the force that causes the particles to go in a circular motion. So QVB equals mv squared on r. Dividing both sides by v, we have QB equals mv on r. So Q on m equals v over rb. So we now have the Q on m ratio. Thomson already knew the strengths of magnetic field and electric field. He could measure R by the deflection, and so he calculated the charge to mass ratio. What are the implications? Well, the first implication is that cathode rays have a negative charge. Secondly, cathode rays have mass. And thirdly, that cathode rays must be particles. Fourth experiment is the Geiger-Marsden gold foil experiment. Now, Geiger and Marsden were led by Rutherford to conduct the gold foil experiment. They aimed a beam of alpha particles at a very thin piece of gold foil and examined the resulting scattered alpha particles using a phosphorescent screen encasing the foil that glowed briefly when hit by an alpha particle. Based on J.J. Thomson's plum pudding model of the atom, Rutherford predicted the alpha particles would shoot through the foil with ease, as shown in this diagram on the left. What did they discover? They discovered that most particles passed right through the foil without being deflected at all. However, some were diverted slightly, and a very small number were deflected almost straight back to the source. So Rutherford recalled this when he said, "I remember later Geiger, or some think it might have actually been Marsden, coming to me in great excitement and saying, 'We've been able to get some of the alpha particles coming backwards.' It was quite the most incredible event that has ever happened to me in my life. It was almost incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." That was Rutherford. Rutherford firstly concluded that most of the atom is composed of empty space. And secondly, he concluded that there must be something small, dense, and positive inside the atom to repel the positively charged alpha particles, giving rise to the nuclear model of the atom. And the fifth and last experiment we need to look at is the discovery by Chadwick of the neutron. Chadwick repeated an experiment previously conducted by Bothe and Becker, where he bombarded a thin foil made of beryllium with a stream of alpha particles that were emitted by one of the radioactive isotopes of polonium. He observed that high-energy radiation consisting of massive particles was emitted from the foil because of this bombardment. The particles were not deflected in either the electric field or a magnetic field, thus they bore no electric charge. The particles caused protons to be ejected from paraffin, thus they must have been as massive as protons. And the particles could not produce the photoelectric effect, Thus, they were not electromagnetic radiation. The newly discovered particle was called the neutron. After Chadwick's discovery, it was soon postulated that neutrons could mediate a nuclear reaction, which eventually led to nuclear weapons and nuclear power production. So our understanding of the structure of the atom has developed with 5 major significant turning points and experiments to back them up, by Crookes, by J.J. Thomson, by Millikan, by Geiger and Marsden under direction of Ernest Rutherford, and by Chadwick. I'm Mr. Mac. Thanks for watching.